Okay, uh, so we want to continue our lesson regarding set theory. So if you remember, the last thing that I talked before the break was so we were talking about the operations between sets. The first operation that we introduced was the union between two sets. And then after that, we started talking about another operation between two sets. That's the intersection of two sets. So let me start reviewing that part a little bit. So this is the notes from the previous lecture. So the definition of intersection of two sets A and B is denoted by this symbol, first of all. So A intersection B is defined to be the set of all members of the universal set such that X belongs to both sets simultaneously. So if this is my universal set and these are my sets A and B, by intersection I mean that part which belongs to both sets A and B simultaneously, and then it is clear that this part represents the intersection of two sets A and B. Then I gave you some simple examples. So for example, this is my set A and this is my set B, and I'm supposed to find the intersection of A with B. It means that I need to go and find the elements which are in common between these two sets. So 2 belongs to set A, and I see that it also belongs to set B, so I am allowed to put it here. So 2 belongs to the intersection. The same thing happens for 3. 3 is in both of them. And the same thing happens for 5. So 5 is also here. But for example, -2 only belongs to A, but if I go and look inside B, I do not see -2, so -2 is not allowed to be in the intersection. And for example, square root of 3 and -1 are only elements of B, but not in A, so I'm not allowed to put them in the set intersection A and B, the intersection of A and B. And then there was a terminology here that is called the disjoint sets. Two sets A and B are said to be disjoint if the intersection between these two sets is the empty set. For example, I can say that if I have the set A equals to this, and then if I have a set B equals to 2 and 3, if I ask you what is the intersection between these two sets, you'd see that there is nothing in common. So this is the empty set, or you can write it in this form, and then A and B are said to be disjoint sets. Another example that I gave in the lecture was the set of irrational numbers and the set of rational numbers. Yes? If I ask you what is the intersection between the set of irrational numbers and the set of rational numbers, of course you immediately answer this is empty, and that's the definition. So what is the meaning of an irrational number? An irrational number is a number which is not rational. So that's also clear that these two sets are disjoint sets. Okay, so let me give an example here. So example. So let A be equal to this set, the set containing the empty set and the singleton containing the empty set, and let B be this set, for example. Okay, then what is A intersection B in this case? So A intersection B is a set, so I need to have a curly bracket on the left, and I have to have a curly bracket on the right. Okay, so this is, and then I need to go and look what members are in common between these two sets. Yes, so here set A has 2 elements, So let me just review these words. The cardinality, do you remember? Cardinality of this set is the number of elements inside the set. So the cardinality of set A is 2. There are 2 elements. One of them is the empty set, and the other one is the singleton, which has the empty set as a member. So I have only two members here. And again, the cardinality of B is 2, but the elements are this set and this set. Is there something in common? Immediately you see that yes, this element is inside A. Simultaneously, it is also inside B. So this is the only element in common between them. So it means that I need to put that element inside the intersection. Okay, so let me just clean this and make it a little bit closer. And this is your intersection, yes? So you need to respect all the curly brackets. The number of curly brackets opened is very important here. Please interrupt me if you have any questions whenever you want to ask, okay? So let me also write a remark here for you. So if someone tells you that X belongs to the intersection of two sets A and B, if you want, you can conclude that X, of course, belongs to A and X belongs to B, yes? That's the definition. The other way around is also correct. So it means that if someone tells you that I found an element X, which is a member of A and B simultaneously, if you want, you can conclude that X belongs to the intersection of these two sets, yes? But now, can you translate this? If someone tells me that I looked inside the intersection A intersection with B, but I cannot find X inside that, what can I conclude?
X does not belong to A and X does not belong to B.
No.
That was for the opposite.
No, I don't understand what's
X doesn't belong to A or it doesn't belong to B.
Yeah, or. This or is important. So X doesn't belong to A or X doesn't belong to B, yes? When you say that X is not in the intersection, of course, it might happen that X is neither in A nor in B. This is one possibility, but I cannot make sure that this is indeed the case. The most thing that I can conclude immediately with just this piece of information is that this X does not belong to A or X does not belong to B. And of course, I told you that this or in mathematics is always inclusive. So it means that it might be possible that X is neither in A nor in B. That's also included, but we cannot say and here. Okay, the other way around is also correct. If you think a little bit, you can convince easily yourself that if one of these things happen, then I can immediately conclude that X is not in the intersection. So this is important to realize that you need to write or here. Okay. Let me go back to the notes of the previous lecture. So if you remember, we had a main theorem. These different parts of this theorem, most of them, are scattered among the exercises in the book, okay? Of course, I don't expect you to memorize them, but if you are interested to learn set theory in a little bit more structured way, this is why I call this theorem. So some of them are actually spread among the exercises without naming them a theorem. So it means that you just solve that problem and you can forget. But if you want to learn it in a systematic way, these are the formulas it's good to have in mind, okay? There is a very similar theorem for intersection as well, okay? So here, if you see in each one of these items, I have the operation, the union operation between these two sets. So if you don't mind, let me just copy this theorem if it is possible, and to move it there and try to write this. Oops, it's not working like that now. So to make it. Yeah, that's better. Okay, so hopefully we can paste it here. Yes. Okay, I can fix that part. So this is supposed to be a theorem for intersection. So that is a similar theorem that we had before for union. I want to make it right for the intersection. Okay, so I would say that let A, B, and C and D be sets, and let U be the universal set. Then we have these things. Okay, so how do you think that I can make the first one right? So what I mean, I want to clean this union and make it intersection. Okay, so then the correct form would be A intersection with the empty set is equal to the empty set. Yes, so I will clean this one and I will write the empty set here. Okay, I don't want to prove this theorem, but I just want you to know different items, and I think that you can immediately guess different parts of that. So for example, how should I change the next one?
It becomes just A if it's A intersection the universal set.
Exactly. So I change this one to intersection, but of course the answer will not be the universal set, but the answer would be the set itself. Yes? And I think based on Venn diagram, it's not hard to realize that. Yes, so this is my universal set, and then I have a set here A, which should be a subset of the universal set by the definition of the universal set. And if I ask you what is the intersection between these two sets, it means that I am interested in those points which lie both in the rectangle and the circular object. So it means that all of them are acceptable, because all these points that you see that I am hatching right now belong both to this circular object and the rectangle. Okay, so this is not hard. Okay, then when I go to the next one, I think this is also easy to understand. So what would be the answer? What is the intersection of any set with itself? Clearly the set itself. Yes? And then I hope that you can convince yourself that this is also commutative. There is no difference between A intersection B or B intersection A. So let me just clean this one as well. So it is commutative. So A intersection with B is equal to B intersection with A. The other one is also associative. So it means that it doesn't matter if I have the, let me clean this and write it again, but I'm just changing the union to intersection. So A intersection B intersection C. This means that the priority is given to this intersection, which is inside the pair of brackets. And then when I find the answer, I intersect it with A, but the answer turns out to be the same if I intersect A with B first, and then find the answer and intersect that new set with C. So exactly like union, intersection is also associative. Okay. Now I think the next one is also very clear for you. If I change this from union to intersection, the answer would be what?
Empty
The
set.
empty set.
The empty set, yes. So this means that the intersect, by the way, you need to read this in English. For example, if you want to read this item in English, you would say that the intersection of any set with the empty set is the empty set. A is just a representative of any arbitrary set. Okay, so for example, here, if I want to read this in English, I would say that the intersection between a set and its complement is the empty set, no matter how I write this set. Okay. Okay, so can you change this one? What do you think? How should I change these two items in number 7?
A intersection of B is a subset of A and a subset of B.
Exactly. So here it's clear when I union two sets, each one of them is a smaller in quotation, yes? So if I union a set with another set, then that set is the subset of the resultant set, yes? But if I intersection a set with another set, I am making the set smaller, again, a smaller in quotation, yes? So a union is a way that I expand my set. Intersection is a way that I limit, I restrict my set to smaller sets. So exactly. So let me just clean everything and write it the other way around. So I would say that A intersection B this time is a subset of A, and of course A intersection B is also a subset of the second component B. Okay, can you just correct the next one, number 8? Here, let me just review this. If I ask you what is A union B, you cannot answer my question unless I give you the sets A and B explicitly with their elements. If I do not say so, if I just ask, write what is A union B, you can just the only thing that you can write is just A union B itself. You cannot do anything. But now, if I tell you that one of these sets, A, is a subset of another one, now if I ask you again the same question, this time you can do better. Even though still you don't know the elements inside the set A and inside the set B, but because of this piece of information, you can write something instead of this question mark for me. And that was the content of the item 8 in this theorem. Okay, this tells you that if A is a subset of B, then if I union these two sets, it becomes the bigger set. And this is also very clear from the Venn diagram, yes? If I have this Venn diagram, this is my universal set. I have two sets. I know one of them is a subset of the other one. So if I want to draw the diagram, I need to respect this condition. So this is the set B, and this is the set A. I have this situation. Now, if I ask you, what is A union B? A union B is all the points which lie either in the circular area of A or in the circular area of B. So if all of them are acceptable, so it means that at the end, all these points are acceptable. But all these points is the bigger set B itself. So this means that if a set is a subset of another set, then union of these two sets becomes the bigger set. But the good point, which we had proven this, is the other way around is also correct. If someone tells me that the union of two sets becomes one of these sets, for example, B, then I can immediately conclude that the other set A is a subset of this set. For example, if I tell you that A union B is A, then if you want to, you can conclude that A is the bigger one. So you can immediately conclude that B is the subset of A. This one was not that trivial. It was easy, but I showed you why this is correct in the previous session. If you have forgotten and you are interested, you can go and watch back that video. Okay, now I want to correct this for intersection. Okay, so if someone asks me what is the intersection of these two sets, I cannot immediately answer unless they give me the explicit elements of these two sets or give me extra information. Now tell me, if someone tells me that A is subset of B, what can I conclude about the intersection?
It's equal to A.
Yeah.
It's equal to A. It's the smaller one. Yes? So A intersection B is A. And this also works in both directions. So if someone tells me that the intersection of two sets is equal to one of these sets, I can immediately, if I want to, can conclude that this set, which is the answer, is the subset of the other set. And I think this item number 9 is also very clear. If A is a subset of B, if C is a subset of D, so we had this situation. For the union, if you want to, you can conclude like this. You can union the left-hand sides. You can also union the right-hand sides. And then if this is true and this is also true, you can immediately conclude that this is also true. So it means that if I have two subset relations, if I want to, I can union them side by side and still that relation holds. Okay, and I think it's not hard to convince yourself that this is also true for intersection, but I don't know, for some reason I had forgotten to put this here. Okay, so let me clean this and write it again. So this means that this time, if I want to, I can conclude that A intersection C is a subset of B intersection D. Okay, so now let me give you an example here. Some examples, okay. Let X and A be two sets such that X is a subset of A and X is a subset of A complement as well. Okay, what can be said about X?
Is X the empty set?
Okay. Yes, the answer is correct. Intuitively, I think it should be clear for you, yes? You have a set which is a subset of this, a set A and its complement. But on the other hand, you know that there is nothing in common between A and A complement. So how is that possible? Intuitively, it's clear that the only possibility should be the case that X is the empty set, yes? Because you know that the empty set is the subset of all sets, okay? But of course, this is intuitively correct. But how can you justify this if you want to prove it a little bit rigorously mathematically? Okay, let me just do it because this needs a little bit of experience. At least it was very good that you all, I think all of you are able to guess that X should be the empty set intuitively. But let me, for example, use item number 9. So you are telling me that X is a subset of A and simultaneously X is a subset of A complement. Yes? I just want you to understand, so this is working, okay? So according to number 9, what can I conclude? Number 9 tells me that if you have two subset relations, if you want to, you can intersect these two relations side by side, and you can keep this relation intact, yes? So this means that I can conclude that X intersection with X is a subset of A intersection with A complement. I just want to wait for you. Is that clear for everyone that based on number 9 and based on these two assumptions, I can write this?
Yes.
Clear for everyone?
Yeah.
Okay, but now can you see what is going on? For example, I can write something for it. What can I write instead of X intersection X?
Just X.
Just X because of number 3. And what can I write for A intersection A complement?
The empty set.
The empty set because of number 6. So let me write this on top of that. So here, based on number 3 and number 6, I can conclude that X is a subset of the empty set. Okay, but on the other hand, do you remember the empty set is the subset of every set? So on the other hand, the empty set is a subset of every set. Namely, we know that the empty set is also a subset of X. So if I write, therefore, what we have now, we know that X is a subset of the empty set. Simultaneously, we know that the empty set is also a subset of X. So do you remember that was the definition? If you remember from the previous sessions, if I want to show that two sets are equal, I need to show that whatever is inside A is also inside B, which means that A is a subset of B, and the other way around. Whatever is inside B, it should be also inside A. So instead of showing that two sets are equal, this is a very standard technique. If you want to show two sets are equal, once you show that the left-hand side is a subset of the right-hand side, and once you do the other way around. As soon as you have these two simultaneously, you can immediately conclude that these two sets are the same. And this is happening here. This we already know. This we learned from the assumptions and the properties in this theorem. So now I have two sets. Each one of them is a subset of the other one. So therefore, I can immediately conclude that X is the empty set. So that's a rigorous way. One rigorous way of showing that X is the empty set, as you were able to guess. Any questions? Okay. Let me give you another example. But this one I want to write and wait for you so that you can use that theorem to solve that problem, okay? But I don't know how can I manage that, hopefully. So yes, so I cannot show these two simultaneously to you. So hopefully you have the intuitive idea of the content of this theorem in your head. So these are important to use, okay? I think you have them in your memory. It's not hard, it's intuitively clear. So let me just write this here for you. So simplify. So yeah, A and B are sets, and U is the universal. Arbitrary sets. And U, the universal set. Okay, so I want you to simplify these items. So number one, so you can start doing them. You don't need to wait. A complement union with the universal set, and then complement. Okay, so let me pause the video at this point. Okay, now let us see what are the solutions, yes? So number one, okay, so what should I do first for number one, any one of you? What's the answer?
The empty
The
set.
empty set.
Yes, the empty set. So I think I was a little bit careless. This shouldn't be here. This doesn't relate to any intersection, but you are right. That's the empty set. So why does that's correct? This is actually the previous lesson, not today's lesson, because that's the union. So anyway, let me just continue with this. So I would say I would interpret this. I have a set, no matter the name, I don't care about its name. I know that this is a set which is being unioned with the universal set. Based on the previous lesson, this union is the universal set. So I would write it in two steps. It's better, for example. So I would write this is equal to the universal set. What I wrote here is the content of this pair bracket, and then I have a complement on top of that, so it becomes U complement. But hopefully you'll remember this property that the complement of the universal set is the empty set. So the answer to this part is just simply the empty set. Okay, so what do you think is number two, the answer to number two?
Also the empty set.
That's also the empty set. But let us do it in using those properties. So the first thing that I want to do is to use the property expressed in the previous theorem. Yes. So if you see here, we know that the intersection of any set with the universal set is the set itself. So this becomes A itself. So let me write it in this form. So the answer becomes equal A. Then let me copy and paste what is coming after that, this part. So this becomes intersection B complement, and then I have intersection with A complement. So if I want to write everything precisely, first I use commutativity to interchange these two. Yes, it is possible. It doesn't matter if I intersect this set with that set or the other way around. So I would write it A intersection. I would write A complement intersection with B complement. Okay. So if you want to, I can write the numbers here, but I don't want to confuse you going back and forth. So that was number 2, and then I use number 4, and then I will use number 5. So 2 here, this is number 2, and this is number 4, commutativity. And then I want to use number 5. So number 5 is associativity, yes? So this tells me that it doesn't matter if I intersect these two first and then intersect it with A, or if I intersect these two first and then after finding the answer intersect it here. So then this becomes equal to A intersection A complement, and then I have intersection with B complement. But now, what is A intersection A complement? If I go here, this is number 6. A intersection A complement is the empty set, yes? So this becomes number 6 now. And the answer becomes the empty set intersection with B complement. Okay, now what is the answer? Intersection of any set with the empty set is the empty set. So the answer is the empty set. If I want to refer the number here, which number is that? And that is number 1 exactly, yes? The intersection of any set with the empty set is the empty set. So I will go back and here, and I can write number 1 here. So you see the properties that I have used to show that this is the empty set is number 2, 1, 4, 5, 6. You see, for this simple calculation, I just want you to understand that all those properties that I have mentioned here, all of them are necessary to be able to conclude that this given set is the empty set. It's very important if you want to study mathematics in the future. This way of thinking would be very handy. Okay, any questions so far?
No.
Okay, so what do you think about number 3?
I think
Should
the
be A.
answer is A.
The answer is A. Yes, I think so. How many of you agree that the answer is A?
Yes.
Yeah, okay. So, for example, the complicated part in number 3, apparently complicated part, is the content here. But this is very easy if you broaden your view, yes? So what's the answer to this one immediately?
The empty set.
The empty set. Why is that? Because you see, I have a set here. Don't look inside. I have a box. And then I have intersection. Then you see the same box repeats itself here. But on top of that box, I have complement. So even though this seems a little bit complicated, but immediately you can conclude that all the content in this pair of brackets is the empty set because it is in the form of the intersection of a set with itself, no matter what is the name of that set. Yes. So let me write it here in this form. So number 3, I would say based on number 6, yes, what was that number? Intersection, yes, that was number 6. So based on number 6, what we have is this: A union B intersection with A union B complement is the empty set. Therefore, the expression is equal to I just write A, I am writing this part, and then I have intersection. And then instead of this expression, I just write the empty set. But on top of that, I have another complement. So this becomes empty set complement. But based on previous lessons, if I ask you what is the complement of the empty set, you immediately answer that is the universal set. So it becomes A intersection the universal set. But just we learned that what is the answer? A intersection with the universal set is the set itself. And that is based on which number? Based on number 2. So if you want to refer to that, you can just write number 2 on top of that. So that would be the end of this problem. So the answer to this part is A. Okay. So let me do the next one. Could you get the answer for the next one as well?
I got it to be the universal set.
Okay, so let us check. So number 4, I see, first of all, I have a pair of brackets. Inside this pair of brackets, I have another pair of brackets. So the priority is with this one. But this is the old lesson. I know that A union, the universal set, is the set itself. So let me just write it here. So this becomes equal to, I copy and paste the first part. And then I have A complement here. And then I have intersection. Instead of A union U, I just put U, the universal set. But on top of this, I have a complement here as well. So I have to put this complement here. But then I continue. Instead of A complement, for the time being, I cannot do anything. I have to write it down. But then I know that what is the universal set complement, and that is the empty set. And then, of course, on top of that, I have another complement. But then if I ask you what is the content inside the pair of brackets, you would say that I have a set. I am intersecting it with the empty set. So the answer would be the empty set. And then I have a complement on top of that. And then, as you said, the answer becomes the universal set. Okay, I just give you one example and I end the lesson right here because you said that you are tired, and then after a long break, I think that is enough. Okay, so I will write an example here and I wait for you a little bit to solve it, and then I will solve it, and when we end the teaching today, but you can be here and work on yourself, and if you have any questions, let me know. Okay, so let me write another example. So let A, B, and C be sets such that we have two assumptions, such that we know that A is a subset of B complement, and we know that C is a subset of B. Simplify the following expression. Okay, so that expression is this one. Okay, so I will wait for you 5 minutes, and then we come back and solve this problem. Did you get the answer? The most simplified version?
I managed to simplify it to A complement.
A complement, I don't think that's correct. I don't know. I haven't checked that exactly. But any other answers? I doubt that this is A complement. Any other answers? Okay, so let us check. Might be you were right. Okay, there are some parts that are easy. Okay, so for example, let us do it step by step. The last bit is very simple, yes? So everyone knows that A intersection A complement is the empty set. So this we know. For this one, I cannot write anything unless I have given some more information. So here I have two pieces of information. I need to use them properly, so that might be I will be able to simplify these expressions. Okay, so can you have a comment on this one? Can I simplify this more than this? In general, no, but might be this will help me to simplify this a little bit more. How can I do that?
Isn't it that since A is a subset of B complement, then B is a subset of A complement?
Exactly. So that is the first starting point. So let me review this. Do you remember when we were talking about subset relation? I told you that if a set is a subset of B, if you want to take complement from both sides, this is wrong. So if I have a subset of B, I can, if I want to, I can take complement from both sides of this relation, provided that I replace them. I interchange the place with B and A. So I would write B complement is a subset of A complement. Yes, and these are, of course, all of them are intuitively clear. If I have a smaller set, compare it with the universal set. So the outside of the smaller set is bigger. yes, compared to the universal set. If I take a smaller set out from the universal set, what is left outside is bigger. So it's intuitively clear, but rigorously you need to realize this. Okay, now you are telling me that A is a subset of B complement. So this implies that I can take complements from both sides, provided that I replace the left-hand side and the right-hand side, yes? So I would write the complement of the right-hand side is a subset of the complement of the on the left-hand side. But then, as you told me, this B complement is B again. This is another property that when we discussed when we were talking about complements of sets. So this becomes this relation. Yes? Now that I know that a set is a subset of another set, if you ask me what is the intersection, I can answer more. Yes? I know that this set is a subset of the other one. So if I ask you what is the intersection, the answer is the smaller set. So the answer is B in this case. So let me just write which one I have used. So if I go to the previous page, I am using this part. If I have two sets, one is a subset of the other one. If I intersect these two sets, the answer is the smaller one. So that's number 8. Yes, I go back now. So here I would write number 8 on top of this. Let me just review it again here. I have two sets. I know that this set is a subset of this one. And now I have to answer this question, what is the intersection between these two sets? According to number 8, the answer is the smaller set, which in this case is B. Yes? Okay, but what can I write for this one? First of all, I can simplify it immediately because I see that I have a set complement, again another complement on top of that. So the complement of the complement is the set itself. Okay, so if I want to write this, then I will have this one. A complement C complement complement is equal to A complement intersection C. Okay, so that's clear. This is at least more simplified than the previous one. But now, can I continue this? First of all, don't get confused because here you have A complement union C, then you have union, this is B, yes? You can do it two different ways, of course. Yeah, we can solve it in two different ways. But let me continue. Can I continue this one more? If I want to continue this one, I need to find a relation between this set and that set. But if I go to my assumptions, the assumptions are relating A with B and relating C with B. But I want to have somehow a relation between A and C. But I can use the transitivity of this subset relation. Yes, how? You are telling me that A is a subset of B complement, so I realize that B is a subset of A complement. And now you are telling me that C is also a subset of B. I can compare these two, yes? So let me write it here. So you are telling me that C is a subset of B. Now from here, I realize that B itself is a subset of A complement. So if you remember, the subset relation has the transitivity property. So it means that if C is a subset of B, B itself is a subset of A complement, you can conclude that C is a subset of A complement. Now that you have this relation, what is the answer to this? Exactly according to number 8, you can write it as a C. Yes? So this is number 8 again. Okay, now everything is ready. So the expression, so let me call this expression I. So therefore, this expression I becomes equal to C union B union the empty set. Yes, is that understandable? Okay, but union empty set doesn't have any role, so I can just write it C union B. Can I continue further or should I stop here? Again, I use number 8. Yes, number 8 for union, not number 8 for intersection. I have two sets. C is a subset of B, and now I am unioning them. So the answer to the union will be the bigger one. So it becomes B. So finally, the answer is just B. Yes? So the answer to this set is B. I don't know, is that understandable? So you see that I am using a lot of these properties. Of course, these kind of questions will not be in the exam, but I just want to tell you that this is also doable at the level of your knowledge, but if you want to learn them. But as I told you, that the items in that theorem are spread around, spread over the exercises in the book, but you don't need to memorize them at all. But this is the systematic way of solving the problems in set theory. So for example, you see what I know, I am just talking abstractly. I have 3 sets. I don't know anything about the elements inside the set, but I have 2 relations among these 3 sets. Then I am able to simplify this expression only based on these 2 information, these 2 pieces of information provided for me. So this big expression is just nothing except the set B if these 2 conditions hold. Okay, any questions? Nothing?
No.
Okay, so I will stop the lesson here. So I think it's good, it's enough here. So let me pause the video.